Hello, everyone. Welcome back to the AAS YouTube channel, and this is part of the good stuff. This is the AAS Journal Author Series, and I'm super happy to have Haley Wahl with us today. Hey, Haley.
Hey, thank you so much for having me.
Well, thank you so much for being willing to talk about your very lovely article, which we'll get to in a bit. Haley, where are you located at?
I am currently in Morgantown, West Virginia.
Morgantown, West Virginia. Has spring arrived in West Virginia?
Well, considering the fact that it snowed about an inch the other day, not really. It keeps going between snowstorm and like 75 degrees Fahrenheit.
Yes.
So a little confused right now.
Yeah, you're getting that battle, right, between the northern colder stuff and the southern warmer stuff coming up. So,
yep.
Well, we'll get there soon enough. I'm in Phoenix. It is March 28th, 2022, as we record this, and Phoenix is definitely entering springtime. I have grapes. I have grape plants off the side of my wall, and I do get grapes off them. And they're all starting to shoot out little buds right now. So they're getting their new leaves and they're ready to do their thing. So I'm excited about spring. So very good. That is a pretty awesome wall of pictures on your background there. What's the inspiration? Why those?
So funny story about those. So I was in my freshman year. I went to the University of Vermont as an undergrad. I happened to take a trip to Barnes & Noble on a Saturday, and there was a picture, like a big thing of Hubble prints in the sale box. And so I happened to grab those and have hung them on every single office wall since.
Cool. Very nice. Awesome. Of course, we're going to be covering a little different wavelength range today. But all good. Speaking of, Haley, what do you like to do for research?
I study pulsars. They are super magnetized, rapidly rotating neutron stars that spin and emit a radio beam. So these are crazy extreme objects. It's like taking something the mass of the sun, crushing it to the size of a very small city that's just a couple of miles in diameter, and then spinning it as fast as a blender. Cool. So things get super crazy. The magnetic field of a pulsar is on the order of 10 to the 12 Gauss. Just as a comparison, the magnetic field of the entire Earth is about half a Gauss. So you wouldn't want to bring your credit cards near a pulsar. So crazy stuff happens near these pulsars, and that's why I like to study them, because they do weird stuff.
Very cool. A fan of weird stuff. Okay, here we go. Let's go ahead, and this is going to bring us to this super lovely article. Open access, anybody, go ahead and grab the article if you want. This is from APJ, the NANOGrav 12.5-year data set, polarimetry and Faraday rotation measures from observations of millisecond pulsars from the Green Bank telescope. And Haley, now that you've had a drink, take us away.
Awesome. Thank you so much. So I just wanted to give a super quick shout out to my co-authors. First of all, we have Dr. Maura McLaughlin, who is my advisor currently, and then Pete Gentili and Megan Jones and Ray Buick help with this a lot. And then we have all of the NANOGrav timers and a couple of other people that really helped with this work. And so huge thank you to all of them. This was a huge paper and a big effort from a lot of people, even though I did lead it. So this is called the NANOGrav 12.5-year data set. Now that means NANOGrav has technically been taking data for about 12.5 years. There are previous NANOGrav data sets. There was the 9-year, there was the 11-year, there is the 12.5-year, there is the 15-year coming up that we're working on. So super keep an eye out for that. There are a couple of different papers that NANOGrav puts out. So NANOGrav, if people don't know, it's the North American Nanohertz Observatory for Gravitational Waves. And so what that means is that it's a big consortium of pulsar astronomers and pulsars around the sky. And so what we're trying to do with those is detect gravitational waves, but you can do other auxiliary science like look at polarimetry with these pulsars. But the main collaboration, the main job is to try to search for gravitational waves. So I've been doing that for a while, but this paper is kind of about the different science that you can do with pulsars themselves while still getting the timing data.
Mm-hmm. Very cool. Very cool. Is this your thesis paper?
It's the main chunk of my thesis.
Okay. Is it Dr. Wahl yet?
Almost. Hopefully in the late summer.
Very cool. Well, I look forward to calling you Dr. Wahl very soon.
Thank you.
You're welcome. All right. Let's do it. Polarimetry.
Okay. Okay. So pulsars, as I said, they are super magnetized, rapidly rotating neutron stars. You can think of a pulsar like a lighthouse. And so as it rotates around, you can see its beam. And so it's kind of like blip, blip. And so it's not in the optical, but instead it's in the radio. And so we use giant radio telescopes to study these pulsars. This paper focuses on the data from the Green Bank telescope, which is actually in West Virginia. I've been there, I think, once. So giant radio dishes. NANOGrav also uses Arecibo, which we unfortunately lost a couple of years ago, but there was a previous paper that did something like this, but with Arecibo data. And so this was kind of the next step to look at the Green Bank telescope data instead of the Arecibo data.
Okay, cool.
So this paper focuses on pulsar light. And so as those radio waves go through the interstellar medium, they get twisted a little bit by the magnetic field of the interstellar medium. So there are dust grains there, and the light gets rotated. And so that depends on how much it gets rotated, depends on things like the charge of the electron and Ne, which is the density of the free electron density along the line of sight, sorry. So, yep, that big expression. And so the delta there is the wavelength of the radio waves. And then you have fundamental constants like pi, the mass of the electron, the speed of light. But all of that boils down to this change in the angle of the light. And so that's really how we do polarimetry. We look at that change of light. And so it's going to change the angle of linear polarization.
Mm-hmm. Mm-hmm.
So the reason why I got onto this project was because polarimetry is something big in pulsars. There are lots of magnetic fields here, lots of radio waves. So polarimetry, pulsars are polarized objects themselves. And so I had no idea what polarimetry was. So I said, hey, let me do a project that's totally about polarimetry. And so I really did a deep dive. And now I think I can say I finally understand polarimetry. Cool. But when we're talking about polarization, essentially it's just constraining the polarization. It's constraining the light along one plane. So for instance, if you have sunglasses on and the sunglasses are polarized, it reduces the amount of light that's coming to your eyes because it restricts it to one plane.
Mm-hmm. Right.
So basic polarization lesson. But what we're really focusing on in this paper is the RM, which is the rotation measure. So it's the amount that the light gets rotated as it goes through the interstellar medium. And so you can use that to do a bunch of science along with the DM, which is the dispersion measure. So it often gets confused. DM is also dark matter. So when I read dark matter papers, I get really confused for a second. And so that's just, it's the integrated free electron density along the line of sight. And so that just measures how much the light is dispersed, which depends on the observational frequency to the -2. But you can see that you've also got this NEL, this integral in the rotation measure equation. And so if you simply divide one by the other, you can get the magnetic field along the line of sight. Exactly. And so you'll see that there's this factor, this beta factor, and that whole yucky expression ends up being about 1. So you simply divide one by the other. And what you obtain is the parallel component of the magnetic field along the line of sight.
Average.
Yes. And so that's a way that to constrain the magnetic field of the galaxy, or just along the line of sight. You can use this RM measurement, which you can get from the polarimetry, and the DM, which is something that we measure in NANOGrav. And so that's going to be in units of microgauss. So it's pretty small. So when the radio waves reach a detector, the light is slightly twisted. And so the way that we measure that light is through this Stokes vector. And so that's the big S. And so you have I, Q, U, and V, and that describes the light in total. So you've got I, which is the total intensity, Q and U, which describe the linear polarization, and V, which describes the circular polarization.
Okay, good.
And so you can also use that to get the position angle of the linear polarization, how much it's changed, by just taking the inverse tangent of U over Q. And so you can see how that angle, how the linear polarization angle changes. So what's going to happen with that light when it comes in is that the telescope and the detector and such, it's going to change slightly. So the light incoming as it goes through the instruments is not going to be the same as the light that entered it. So the light that we receive and that we record is not going to be the exact same thing as what came in. And so what we have to do is essentially we have to untangle that. So this is M, it's called the Mueller matrix. It's this big, I don't think I have it in this paper, but it depends on a whole bunch of stuff like certain angles and such, but it's a really messy kind of equation. And so it's really messy matrix. And so what we have to do is, again, we need to untangle it. We need to untangle that Mueller matrix. We need to get, in order to do any kind of interstellar medium studies, is we need to figure out what the light was like before, as it entered the galaxy. So correct for the instrumental response.
Yeah, good.
And so that's where polarization calibration comes in. So what we were doing, so there are a couple of different ways that you can do polarization calibration. Calibration is really necessary in pulsar science and usually in a lot of different things, just to make sure everything's going well and just to make sure that you're getting all the parameters you need and that they're what you expect them to be. And so we do a super basic flux calibration, which is just taking essentially what it does is it brings the information from telescope units, like counts, and makes it into something that we can understand, like intensity. And so Jansky's is what we use in astronomy and in radio. But polarization calibration is needed to get the actual polarization information out of the telescope. And so we do, sorry.
No, good, I'm with you.
Okay. So we do a basic polarization calibration in NANOGrav involving a noise diode and a very polarized source. We use a quasar for this, but all the NANOGrav data does this. But in so there are a couple of really robust polarization calibration methods, and one that we use is it's called matrix tempo matching. And so we take long tracks of observation. Sorry, I'm kind of going out of order here. I'm kind of bouncing down to the methods here. But thanks.
Here we go. Calibration method. Here we go.
Yeah. Yep. So we take a really long observation, this was data of 1929 plus 10. It's a very stable pulsar. And so we took that. So actually, this was another team that took that data and observed the pulsar from rise to set. And so as long as it was up in the sky, and so as long as the instrument could handle it. And so what we did was we took observations like that on a couple different days and corrected for the instrument's response on all of those days. So I think it was about 5 epochs. And so we solved for a solution, solved for the Mueller matrix. I don't actually have to do that much math. There's a program that will actually calculate this for you if you just put in a couple things. So it's not as nasty as it sounds, but so we get the Mueller matrix out and we get the solution for those days. And we use that to calibrate the data. So essentially, again, we're kind of untangling the solution and trying to get the light at the beginning. So I'm just kind of looking through the papers, seeing what I want to cover next. So that's what we did. So we have about 23 pulsars that we looked at. So we have more than that in the NANOGrav data set. So, but some of those are observed just at Arecibo. And so they're not in quite the correct declination to be used by the NANOGrav data, by the Green Bay telescope. We can't see them. Right. So this was 23. So we calibrated observations of all of those pulsars. We have these pulsars are observed for the NANOGrav data set on roughly a monthly cadence, with the exception of 1713, which is a really bright pulsar, which has actually been misbehaving lately, but that's a different story. And 1909, which they were both observed weekly starting in 2013. Yes. So lots of pulsar observations. We have actually up to, so the title, it might be a little bit misleading, but we have up to about 4 years of data for all of these pulsars. No, it's called the 12.5 year, but we noticed toward the beginning that when we were looking at the rotation measures and correcting for them, that they looked weird past a certain day, like they were going all over the place. And so we figured out that around that date, there was a sampler board switch for the Green Bank telescope. And so that kind of threw everything off. And so we couldn't quite use the rotation measure past that day. And so we didn't think they were super reliable, but it doesn't affect the NANOGrav timing. I've done a couple of analyses, and it shouldn't affect timing at all, shouldn't affect total intensity. But that did kind of shorten our data set, which was kind of annoying. But the paper is called the 12.5 year because the data was treated with methods that were actually used in the 12.5 year. And so we couldn't call it a 4-year data set because these methods that were used to treat the data sets, such as zapping and some calibrations, weren't developed back then. And so we keep it at 12.5 year to specify that there were 12.5 year methods used on it.
Got it. Okay.
Yeah. Yeah. I had to step back for a second and think about that when I did it. So, yep. So we saw for receiver solutions, that's what I think figure 1 is. You just have a couple of parameters. I think figure 1. Yeah. And so that's what a receiver solution looks like. May not look like much, but it's just essentially telling us the stability of the receiver. And so if you do that for, I think it's all 5 epochs that we use, an epoch just refers to a day. So 4 epochs of data are 4 days of time. I don't know if everybody uses that terminology, but
we are.
So you can use that. So we work in MJD, which is modified Julian dates. And so you have things like the cross coupling of the receiver, the ellipticity of the receiver, the differential phase. And so just a whole bunch of instrumental things. But if you look at these over the course of 5 different epochs, they look pretty stable.
Cool. Good.
Yeah, so things were all good there. And the main conclusion that we drew based on plotting those solutions was that things are relatively stable. Things don't change a ton over the course of, the 4 or 5 years that we were doing. So everything was pretty good for that. So when we corrected for rotation measure, so the way that the software, it was just called PS Archive, was the way that it does it is it essentially finds the max of a linear polarization and then fits it. And so that's what you're going to see in figure 2 is you're just going to see this curve, and it's looking at a certain rotation measure. And so it's going to find that peak. And so where the linear polarization is the highest, and it's going to try to fit that peak. And so that's called, so you can put in a range and it'll fit it for you and get out the rotation measure. And so sometimes these are really tricky because if you have a really low signal to noise profile, you can't always get a fit that's like this. And so sometimes it actually won't because it's really messy and really hard to fit. Sometimes you have to play with it. But so that's the method that we use, and then it slowly refines it and will get you your correct RM. So we have a pipeline that does that. So before you can actually do science with this, you need to, before you can look at the magnetic field of the galaxy using this rotation measure and dispersion measure, you need to correct for the ionosphere. So for anybody that doesn't know, the ionosphere is just the big kind of blanket in the atmosphere. It's a bunch of magnetic particles and such that, things like, so you can, magnetic field. So there's a big magnetic field, essentially a big magnetic field in the atmosphere. So the light will go through that and then it'll get slightly twisted, not much. It's only like 2 to 5 radians per meter squared, but you need to correct for that if you want to really get correct magnetic field of the galaxy. And so that's something that we had to do afterward. There's a really great code developed that does that. And so we, by Charlotte Sobey et al., that will do that. And so by doing that, we could get out the actual rotation measure as the pulsar light went through. So I haven't talked about DM a lot. So dispersion measure, again, not dark matter, as the pulsar light goes through the atmosphere. So the DM could be measured. We actually do. So there's a parameter called DMX. The X doesn't really stand for anything, but essentially we measure the dispersion measure. I think it's about every observation. And so once every maybe couple weeks, And what you can do is you can match those to the pulsar observations. So they may line up, it may be like a day, but we don't really expect the DM to change that much within a day or so. So you can match those, the RM measurements, and just dividing the RM by the DM, multiplying it by a small factor, you can get the average magnetic field along the line of sight at that point.
Yep. Okay.
So that's what we did.
Here for 23.
Yeah, exactly. And so, sorry, I'm kind of jumping all over here, but if you go down to probably like the last figure of the last couple,
Sure.
you can really see this.
Let's slide down. Let's take a look, for example, at
Yeah. And so if you look at, I call them triple plots. So if you look at any of these pulsars, what we did, okay, yeah, for instance, take 1909. And so you can calculate the magnetic field. Again, that's the rotation measure over the dispersion measure. And so I kind of centered these out just by subtracting the average. And so you can see what these plot is you can just zoom in on one, is the difference from the mean. And so how much it varies over the time from the mean. And we did that for dispersion measure as well. We didn't do it for rotation measure. We originally did, but that magnetic field, so the dispersion measure changes are going to be really small. And so everything is kind of reflected in the magnetic field calculation. And so again, yeah, you can see this change in dispersion measure is really, really small. These variations are, on the order of 10 to the negative 3 parsecs per cubic centimeter.
Yeah.
And so, yeah, so what we did for all of them, so we actually have two different frequencies that we did. I forgot to mention this, but we have 820 megahertz and 1500. So we did them same general technique, just solving for the Mueller matrix, but 1500 megahertz, we had only one solution that we could do. 820, we had 5. But everything is essentially the same for these. And so just looking at the different frequencies and seeing how they vary, there aren't huge discrepancies in the frequencies. And so that's something that we kind of expected. But so there are kind of two parts to this paper. There's first of all, the polarization calibration and then things that you can do, but also kind of the pulsar science you can get out of it. So just keep going on this. So you have these magnetic field trends and you have dispersion measure. Sometimes you might be able to see a pattern if you squint. So we tested a couple of different things. So we tested a linear trend, which if the pulsar is moving away from us or going toward us, there might be a linear trend in magnetic field or dispersion measure. We also tested a sinusoidal function. So if something's varying over the course of a year, we might have something. And then we tested both. So if the pulsar is moving away from us or moving toward us, and we also had some kind of yearly trend, and that would show up. We didn't do anything other than a sinusoid and a linear trend, just because we didn't really think that those physically made sense. And so we don't want to fit anything to like a fifth order polynomial, just because we didn't really see anything physical with that. So there's really no use to it. And so that's what we did. So all of the fits were done with the least squares fitting technique, and all of the sinusoids have a false alarm probability less than 5%. So we really wanted to make sure that these are true. So that's what we did for all of these pulsars. We didn't find out anything major. So again, these are about 4 years of data max for each pulsar. So we didn't find anything huge. Some of the magnetic field trends, though, there might be a linear trend. And so what we did with that is a linear trend would mean, so we took the distance that the pulsar would travel from the time that we started the observations to the time that it ended. And so figured out the distance that should be traveled, figured out the magnetic field that should be within that distance. And so we calculated that. And the magnetic field values that we were getting for the slope were way larger than they should have been, way larger than that ambient magnetic field that would have been within the line of sight. So that means that these pulsars must be traveling through some kind of magnetized clumps in the interstellar medium. So there's got to be something magnetic between there if the magnetic field is way bigger.
Good. I'm with you.
Great. So that kind of takes care of those plots, if you go up to, I'm just going to go through the tables real quick. If you go to table 1, you can just see the start and the end of our observations. Yeah.
Get there. Oh, it's table 1. Okay, got it. Yep.
Yeah. Sorry, again, I'm kind of jumping around. So you can see we added some pulsars late to the data set, and they might have a different start date. Some, like 1713, we've been observing for a really long time, and so we have a ton of observations for these. So these are the total observations that were used. We had to take some outliers out for various reasons, but these are all the observations that we use. And so if we had less than a year of data for the pulsars, we didn't include them in that B field and that DM plot. So we didn't, if they were to show trends over a year, great, but we didn't really think that there's anything that we could do with pulsars less than that. So there are a couple that are really short observations. So we can go down to table 2, which has a bunch of information in it. You have a ton of things like distance, just general dispersion measure, rotation, so both corrected and uncorrected for the ionosphere. And then you have magnetic field, again, micro Gauss. And so you can see that some of these, you have a couple that have like a really highly negative D or RM. And so something like 1643, that's because J1643, it's in the middle of, I think there's a big H2 region in front of it. And so you've got all kinds of stuff going on there.
That's huge and negative. Okay.
Yeah. Wow. Yeah. And so that's just you can have negative magnetic field. It just means the sign of a magnetic field. And so whether it's like right-handed or left-handed. And so if you go down to figure 3, you can see the value of the magnetic field at certain places. Gentili et al. Is the one that did this with Arecibo data. And so you can see just the differences in those. There isn't kind of a clear, it should be negative here, it should be positive here. It's a little bit anisotropic, but those are just the values compared to the other values on the sky.
Which kind of speaks to it being a local effect as opposed to something ordered and global and across the galaxy.
Possibly. So the location of those triangles and those dots are just the locations of the pulsars, and so we can't observe pulsars. Like there aren't really good pulsars at like -90 and such, and so we just don't have pulsars on the sky to measure over there.
Fair enough. Okay.
So the next part that I'll get into is a little bit of the polarization of the pulsars themselves. And so if you go down to table 3, now actually going in order, up a little bit. So you can see the amount of polarized intensity of the pulsar. So again, P is the total power, and so the total fractional polarization. So you have L, which is the linear polarization, and then V, which is the circular, and then the absolute value of V, which is just the absolute value of the circular polarization. And so you can see some pulsars are super polarized, some are not. If you go down to figure, it's like 6 through
6.
The blue and red plots.
Blue and red plot 6.
Blue and red plots.
There's blue and red plots.
There we go. So if you just scroll through them slowly, so the red is, or the black is the total intensity, the red is the linear polarization, and the blue is the circular polarization.
Oh, nice.
So you can see there's the one on the left is going to be the 820, and the one on the right is going to be 1500. So there's a lot of variation. You have a lot of different structures in these these pulsars, but one thing that's really unique to this data set is that these are some of the highest signal to noise observations of these pulsars, and certainly some of the highest signal to noise polarization pulsars that we've ever seen. So these are really amazing observations, and so we can see a lot of structure in these. For some of them, it's the first time these polarization profiles have ever been measured or have ever been seen, and so there's a lot of stuff that we can do.
Wow. Okay.
Yeah, so there's a lot going on here, and so you can see there's a huge difference in the polarization. I want to point out the arrow on 1024
Okay.
So this points to kind of, if you scroll down a little bit, that's just a zoom in. And so one of the coolest things for me that we looked at in this paper is micro components.
Okay.
So pulsars in general, we think that they have some kind of core double cone model. And so as your sightline goes across the pulsar, you'll see parts of these cones. And so that determines how many components you're going to have in the average profile. And so that's for just pulsars in general. I forgot to mention that there are actually two types of pulsars. There's canonical and there's millisecond pulsars. Canonical, born in a supernova explosion, just the end of a big star's life. And so that will have, it's just kind of the end of a star's life if it's not heavy enough to become a black hole. But millisecond pulsars are kind of like zombie pulsars. And so the pulsars lose energy over time. And so as they spin down, they will lose that energy and spin slower and slower. If they have a binary companion, which a ton of stars do, then it'll steal mass off of that. And just with angular momentum, it'll spin it up and it'll spin much faster. And so you have these crazy fast pulsars that have spin period that spin, multiple hundred times a second. And so they're crazy. And so we think that canonical pulsars generally have this core double cone model. But once we looked at millisecond pulsars, that kind of goes out the window, because you can see probably if you go up on 0740 or not, 1012, that doesn't look like five structures. That, like, they're just weird. And so we think that has to do with the magnetic field configuration. It just gets all messed up in the secretion process. And so these little microcomponents, which were actually detected in Gentili et al. 2018, are super small components that are, I think it's like less than 3% we calculated of the total intensity. And so these are super weird. And we see them in some bright pulsars. I think if we had a higher signal to noise, and if we had more time in these observations, you could see them hopefully in all pulsars, maybe not, but you can see that the emission is not localized to this one profile. You can't really tell where the duty cycle of a pulsar is kind of when it's on and when it's off, the amount of time that it's emitting. It's not really clear here. And so it's not the time a pulsar is on and it emits is not super clear. And it kind of throws our ideas of pulsar emission it throws them off, because where are these things coming from? Are they coming from the cone? Are they coming from a patchy beam model in the pulsar? Kind of what's going on here? And so I think that those have been one of the coolest parts of this paper, is just finding those and examining this.
Very cool.
Yeah. So those are pretty awesome. If you go up to table 4 again, just trying to cover a bunch, you can see where these pulsars have been observed before, if they've been observed a lot. Some of these pulsars have been pretty well studied, some of them have not. And so these are the first polarization profiles for a couple of them.
Okay. Cool.
Yeah, so something like B 1937 has been very well studied, and 1713 is a really bright pulsar. But some of these other ones, we can see the first polarization properties from them, and so it's been pretty cool. Yeah. So pulsars are thought to evolve, like the emission structures, or the profile is thought to evolve over the course of frequencies. So sometimes at low frequencies, it will be one shape, then it'll evolve to another shape, kind of like going back to the profiles. We don't really see that in millisecond pulsars. So again, that just points to the emission being weird. These tables cover, sorry, I should have mentioned these when we were talking about the trends, but just the trends that we fitted in each, the slopes, if we had a linear trend, the amplitude, the period, the reduced chi-squared, which essentially quantifies the fit, and the pre-fit, which just compares it to a straight line, and then the false alarm probability. And so you can see that it's a good chance that these are not fake trends; they are actually real.
Cool.
So, yep. So you talked about dispersion measure variations, variations in magnetic fields. There's a lot of work has been done on this for other data sets. There are big pulsar telescopes in different parts of the world, for instance, Australia, Europe. And so a lot of this work has been done with other data sets, but this is the first time that things have been done with the NANOGrav data set for the Green Mag Telescope. One really cool thing that I think, again, one of the coolest parts of the paper for me was that within the outliers, so if something had like a big rotation measure, like a huge rotation measure that was more than 3 sigma off, we threw it out because it, we didn't think it was real. It must have been some equipment malfunction, something went wrong. But we checked those rotation measures and we checked the dispersion measure outliers and we found one that had a huge spike in rotation measure and a huge spike in dispersion measure around the same time. And so we looked more at that pulsar and found that those occurred when the pulsar was pretty close to the sun. So just the angle of the pulsar and the sun was really close, and actually got to measure the solar galactic magnetic field right there.
Right.
Which was pretty cool. And so we found that it was consistent with what was in the literature. And so I thought that was just kind of neat, just taking something that we're just going to throw out and actually measuring the magnetic field of the sun. Mm-hmm. So I thought that was pretty cool.
Let the probe folks know.
Yeah. So we tried to see, kind of going down to section like 4.3-ish. I don't think I missed any big figures. So this was the first time that some parameters some of the polarization had been looked at for these pulsars. And so we tried to see if it was correlated with the age. So if older pulsars had more polarization than others, if the spin period was correlated with it. Didn't really find anything. We didn't really expect to find anything, but it still would have been cool if we had.
Yeah.
So I think we just need a larger sample size just to make sure that nothing's going on. It would be cool if we found something though. So going back to NANOGrav itself, one thing that we are really interested in is trying to detect gravitational waves. And so how does polarization affect the times of arrival of pulsars? Okay. And so there have been a couple studies done on this. So a couple of people in various parts of the world doing things with various pulsars have done this and have found that it could make a difference. And so the biggest one that was done, there was a study done by Axel Rogers in his thesis, in his master's thesis. And what he found was that using a bunch of different techniques to do polarization calibration, for instance, using things like the ideal feed assumption, which assumes certain things, and just using different methods. For instance, the scalar template matching just uses the total intensity, and then the matrix template matching is what we do, and then matrix equation matching is another thing where you force the profile to look like an ideal profile. So there are just a couple ways that you can do this, but what he did was he looked at all of these different things and found the best method to do it. And so that drastically improved the times of arrival in some of these. So the residuals, which are the difference between the measured and the theoretical, they were greatly improved. And so there was a much smaller difference, and things were really improved. So that definitely is something that we want to do with NANOGrav in the future, is just look at the effect of polarization calibration on observations.
Yep. Yeah, that's pretty very nice.
Yeah.
Okay.
I think I think I covered everything. Yeah, if you just look through it, the profiles, the red and blue plots there, some of these have super interesting structures. One thing that I didn't touch on is the polarization angle. And so if you go up to figure, I think it's like 6 through 13 roughly. So you can see the polarization angle is the very top panel. And so in regular pulsars, we think that looks like an S. And so as the beam kind of goes through the magnetic field, and it can look like an S shape, which is consistent with the rotating vector model, but you see a lot of weird things in these pulsars, like they don't follow that. So again, it's just harder.
I use my imagination, it might be S.
Yeah. So if you go to something, they're crazy looking, and so that just confirms that the magnetic field structure kind of gets all messed up. But so they're not the same as canonical pulsars. They're much stranger, much harder to study. Yeah, so that definitely doesn't look like an S shape. Still interesting to study, and so you can't really constrain the emission geometry too much with these, but you can look at the magnetic field and do a whole bunch of polarimetry with this.
Cool. Very
yeah,
nice.
they're definitely interesting to study.
Very awesome. Haley, thank you for walking us through this very lovely article.
Of course.
And you touched on it a little bit as we were talking through. And so I will ask, where do we kind of go over the next 2 to 5 years? You mentioned the NANOGrav 15. Let's roll the dice for NANOGrav 20. So just sort of, where do we go, let's say, over the next 2 to 5 years, either on these pulsars or other pulsars or other facilities, other polarization studies, etc.?
Yeah. So my next project, which I kind of alluded to at the very end of this, is taking these polarization calibrated profiles and running the NANOGrav timing pipelines on them and looking at the effect of polarization calibration on the NANOGrav TOAs. And so kind of wraps up my thesis nicely, but just doing that and working on the pipelines for that. It's taken a little bit of time, just making sure all the software is up to date. But yep, so that's for me. But in terms of NANOGrav stuff, unfortunately, we lost Arecibo, and so we're trying to get data elsewhere. There are a lot of pulsar facilities around the world that are doing a lot of really cool things. FAST just came online, and they're in China getting amazing observations. The European Pulsar Timing Array is doing a ton of cool stuff. Clark's Pulsar Timing Array is doing a ton of stuff, just really trying to search for these gravitational waves, which we may have been seeing hints of, maybe may have been seeing a signal, but definitely keep your eye on gravitational wave science in the next couple of years, because there are so many auxiliary studies with dark matter, studies with continuous waves and supermassive black holes, just really cool stuff. So definitely keep your eye on pulsar timing arrays in the future, because they can do a lot of really cool stuff. Measuring the mass of neutron stars, 0740, I think from Cromartie did a lot of work on that. Just really cool stuff that you can do with pulsars. So definitely keep your eye on the field.
I shall. Very cool. Haley, thank you so much for walking us through your very lovely article. And that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.